the equivalent resistance across the points A and B, where each of the resistances shown in the figure have the value of R ohms. What is coming to your mind when you see such kind of a problem? Do you think that this must be a very difficult problem? Do you think that this will take a lot of time to solve? No worries. This is where I come. Hello everyone. This is Dr. Arjun Ghosh, Isha ma'am. To help you solve this problem, and not only this problem, I am going to talk about a concept using which you all will be able to solve these kind of problems very easily and in a very short time. So, let's begin. The concept based on which I am going to show you solving these kind of problems actually talks about balanced bridge or a bridge in a balanced condition. So let me first talk about balancing of bridges. Namely today the bridge which I am going to talk about, or I will take the help of the bridge, Wheatstone Bridge. I am sure that you all must have learnt about Wheatstone Bridge in your earlier days. However, I am going to give you a very brief recap about Wheatstone Bridge. So first let me draw it out. We draw a Wheatstone Bridge something like this, where let the name of these resistors that we are using is P, Q, R and S. Say across these 2 points, generally I am going to say we can apply some voltage across these 2. Fine. Now, this is the overall or the preliminary picture of our Wheatstone Bridge. However, I have not drawn a very significant instrument over here, which is called a galvanometer. Reminding all of you, what is a galvanometer or what is the use of a galvanometer? Galvanometer is the meter which we incorporate in a circuit when we have to know that whether there is any flow of current or not. So when I have put this galvanometer across these 2 points, when I see that there is deflection in the galvanometer between these 2 points, the inference that I will draw is that current is flowing between these 2. More the deflection in the galvanometer, I will take the inference that more current is flowing through them. However, if this galvanometer shows us null deflection, which means it is not showing us any deflection, the meaning is that no current is flowing in between these 2 points. Okay. Now, in this Wheatstone Bridge circuit, as you can see over here, as per the Wheatstone Bridge principle, if the ratio of these 2 resistors P and Q, the ratio of P and Q, if that equals to the ratio of R and S, my dear students, when these 4 resistors follow this equation, when they satisfy this equation, we call that this bridge is in a balanced condition. And how does it manifest? It manifests in zero deflection of the galvanometer, which means when the ratio P by Q is equal to R by S, no current will flow between these 2 points. Let me call these 2 points say like A and B. Okay, so no current flows between A and B when the ratio P by Q is equal to R by S. Okay, so this is the principle of Wheatstone's bridge. However, why am I telling you this in order to, why I was talking about this kind of a problem? Now let me show you. Remember, the clue that we were given was that each of these resistors in the circuit are having the value of R ohms, which means each of them is equal. Now take that clue from here and let us try to see what will happen if I prepare a Wheatstone bridge with all the resistors to be equal, that is P is equal to Q is equal to R is equal to S. Then I hope all of you will agree with me that in this condition, when all the 4 resistors are equal, this bridge will perpetually be in balance, correct? Which means there will never be any current flow between these 2 points when each of these resistors are equal. My dear students, now think of one condition. When I say that no current is flowing between these 2 points, am I not also meaning that there is no potential difference between these 2 points? just reframing my sentence. Between A and B, there is no potential difference, which means if there is no current, if I is equal to 0, as shown by the galvanometer in this condition when the bridge is balanced, what can I say? What can I also say? That the potential difference between the points A and B is also equal to 0. Right? And in a circuit, when there are 2 points where there is no potential difference, it essentially means that these 2 points are basically short-circuited. Getting my point? What did I tell? I'll repeat once again. When these resistors P, Q, R and S are all say equal, or they are following this particular equation that P by Q is equal to R by S, in between these 2 points there is no current flowing, which means there is no potential difference between these 2 points, and hence they are as good as being short-circuited. Right? Now see, this particular idea, please carry it with you, that when a bridge is balanced, when something like this picture that you can see over here, when this square figure is balanced, these 2 points can be considered as short-circuited. Correct? This very concept we are going to take from here and then use it in our given problem. Okay? So let us see. I hope all of you are still remembering the concept of Wheatstone bridge. In a balanced bridge like this, these 2 diagonal points, in between these 2 diagonally connected points, there is no potential difference and hence they can be considered to be short-circuited. Fine. So now let us go back to our given problem with which we started the video. Look into this circuit once again carefully. Can I not say, I hope all of you will agree with me that this small little square over here is just the replica of the Wheatstone bridge over there. We had P by P, Q, R and S. So this is a small Wheatstone bridge and it consists of so many others as well. Right? So, the clue that we already have is that all of these resistors are of the value R-use. Which means, if I consider this small little part of the circuit of this figure, that is balanced. Correct? So, if that is balanced, we can consider that these 2 points are short-circuited. Which means as if I have connected them with the help of a wire. Right? Similarly, I hope all of you will agree if I say that these 2 are also connected and these 2 are also connected. Like this, we can draw imaginary wires connecting these points. Why am I saying imaginary points? That essentially we do not require real wires to short-circuit them. They are already short-circuited because of the condition of the bridge being balanced. But we are drawing this so that our picture becomes very clear and our calculation gets very, very easy. Now the moment that we have figured out that in real these points are short-circuited, now I will show you that our problem has become so simple. Now see this. Forget about the rest of the circuit. See only this one. What do I have? I have this, but I know that they are now connected. So which means if I draw it like this, is it not equivalent to drawing 2 resistors which are joined in parallel? This is R and this is R. So this small triangular part that you can see over here is equivalent to 2 resistors joined in parallel, given that these 2 resistors are having the resistance smaller. Correct? So, reminding all of you, this is like a very, very preliminary thing, that how do we add up resistors or how do we find the equivalent resistance across, say, this point A and B. See, if this, the equivalent resistance is, say, R1, what can we write? We can write that 1 by R1, let me write it really carefully, 1 by R1 will be equal to 1 by R plus 1 by R, which means 2 by R. And hence, the equivalent resistance across A and B, which is R1 is actually equal to R by 2. Yes, students, I hope all of you have followed what I have just said or what I have just done. So, the effective or equivalent resistance of this part of this circuit is actually, say, let me just write it down. This part was R1 and we found out that to be R by R1 is equal to R by 2. Fine. Now let us move forward. Now look at the next part of the diagram. How many resistances do I have here? 1, 2, 3, 4. Now see, it is as if we are having two lines or rather two wires, and across these two we have joined something like this. I hope all of you can follow. This is what we are essentially doing. So these are all R. So when I have connected them basically to a common wire like this, what have I done? These four are essentially nothing but joined in parallel. So this is again just like these two were connected in parallel with each other. The next four are also connected with each other in the parallel manner. Correct? So can I not write that what will be the value or equivalent value of these four parallelly attached resistors? So as of now I have four resistors connected to each other in the parallel manner. And obviously, if I say this value is R2 across this point, this part of the diagram, if I name this equivalent resistance as R2, what will be R2? 1 by R2 will be equal to 1 by R plus 1 by R plus 1 by R plus 1 by R. Correct? Which means 4 by R, and hence R2 comes out to be by 4. Isn't it? I hope all of you are agreeing with me and are following what we are doing. Right? So, from this part of our discussion, we have seen that this part of the circuit, this part of the figure rather, this part of the figure has an equivalent resistance of R by 4. Now like this, we can just repeat our calculation because they are the same. Here we had 1, 2, 3, 4. In the next part also we have 1, 2, 3, 4. So if I am dividing like this, if I write this as R3, what will that be? 1, 2, 3, 4 resistors of value R ohms connected in parallel. What will be the equivalent resistance? Obviously, this also would be R by 4. Moving forward, this part also will be 1, 2, 3, 4. So there are 4 resistors of value R connected in parallel once again. So R4 also will be R by 4. And we will repeat this entire discussion for the next part also. Here also we have 1, 2, 3, 4. So if I call this part as R5, that too will be R by 4. And we have come to the end of this particular figure, where again I am left with only 2 resistances just like the first one. So if this is R6, what will be the value? I hope all of you will unanimously say that this is also going to be R by 2 because there are 2 resistances connected in parallel with each other. Now yes, we have come to almost the end of the problem. So what do we see? What are we seeing over here? Individually, when we have calculated all of them, we have already got their values. However, please think, how is R1 connected to R2? R2 is connected to R3. How are all these individually connected to each other? They are connected in series. Simple. So if I now go back and ask you the same question, that what is the equivalent resistance between the points A and B? What will you say? The resistance across A and B is nothing but the addition of R1 plus R2 plus R3 plus R4 plus R5 plus R6. And that is simply equal to R by 2 plus R by 4 plus R by 4 plus R by 4, one more R by 4, and the final one was R by 2. Right? R by 2 plus R by 2 will give me R. These 4 R by 4s when added will give me one more R. So my final answer will be 2R. different resistance across the points A and B for the given figure, for the given set of resistors connected in this manner is nothing but twice of R, when each of these small resistors are having the value small ohms. So our answer finally is coming out to be twice R ohms. Right? Do not forget to put in the units, because in the beginning we were given the unit. Right? So I hope all of you have understood how we have done this problem. Now just take a break over here and try to think. Once we have identified that these 2 points are as if short circuited, that means we have remembered or we have utilized the concept of the balancing of a bridge. How long did it take us to come to this answer twice R ohms? It was less than even a minute. Am I right? So this is the concept, or this is the trick that I want all of you to understand and use whenever you are given problems like this. In most of such kind of problems, you will always come across circuits or rather a part of the circuit where they will always give you similar value of resistances only. Right? All of them will be 1 ohm, 5 ohm, 10 ohm, like that. And you can very easily use the concept of a balanced bridge. And hence, you can always do these kind of problems in a very, very short time. So, I hope this video was helpful for you. And if it was helpful, please show this to your other friends who might also find it useful. So, share the video. And if you liked it, do like it. And 80% of the viewers of my channel, as I was looking through my analytics, I found that 80% of the viewership was coming from non-subscribed viewers. So this is my humble request that if you find the videos in my channel useful, please subscribe to the channel and also like and share videos which you think might help others as well. So that's all for today. I hope all of you are staying safe. Bye bye all of you. Take care.